So I am pleased to introduce Professor Yannick Hoarau, who is professor at the University of Strasbourg. He's working in the research unit EQ. He's director of the mechanical department, and he will present the work on numerical modeling of electro-active morphing on wings. So Professor Hoarau.
Thank you, Professor Raymond. So yes, I'm going to talk today about fluid mechanics, but also on a little on solid, because we are going to play with solid actually to try to control the flow along wings and to do, the idea is to improve actually the behavior of the flow and to increase the performance of aircraft. So this work is an ongoing work since more than 7 years now with a lab in Toulouse, IMFT. And it was part of a European project, an ANR, and now another European project. So, what do we want to achieve? If we look at the first aircraft, the one designed by Clément Ader, the first one that was able to fly, actually it was a bat. Nothing like the aircraft of today. Today there are also some reconfigurable drones that exist, and the idea always with this... C'est trop fort? The idea behind actually is to try to mimic birds. The best flyer will always be birds, and we want to mimic the birds, and the birds actually they have the faculty to move their wings, their winglet, their leaflet, and so on to adapt to any kind of situation. And we want to do something like that using actually electro-active morphing, and I'm going to explain what it is. So there is also a project, for example, by Airbus, which is called Bird of Prey, where they try to build an aircraft that is really similar to a bird with morphing, meaning movable wings and controllable wings and so on. So what are the phenomena that we encounter when we deal with aerodynamics, with aircraft? We have wake instabilities that appears, and the wake actually, even if it's far behind the aircraft, it will have an effect on the performance of the aircraft. You have the buffeting, so the buffeting is a phenomena where you have high velocity, so basically when you have an aircraft in cruise mode, you have a shock, and this shock may oscillate. This is something that you don't see when you are in an aircraft, because if it happens, you have what we call the Dutch hovering. So basically the aircraft is going up and down, up and down, up and down, and after 5 minutes everybody is healed. So that's not what the pilot and what you don't want to do, but what is interesting is that usually this area of flight is something which is interesting, because it's beside the fact that you have this oscillation of the lift, you have the best performance of the aircraft. So we would like to reach this without the buffeting. Today's aircraft, you have very deformable wings, so you have also flutter phenomenon, so an fluctuator interaction where you have the flow that will give deformation of the wing that will modify the flow and so on. And also, the dynamic source, something that you don't want to encounter, is a huge detachment of the flow. So, I'm going to present very briefly the smart and morphing project, the numerical method that we use, and the different results that we have achieved in the last years. So the beginning of this project, the main part was an European project that started in 2017, and it contained 10 European partners, and the idea was to build something that could be put on an aircraft, and that also could be autonomous. In terms of electro-active morphing, this is the work that has been done at Laplace Laboratory in Toulouse, and it is something that it is sustainable. So we can put all the electronics, all the mechatronics, all the power converters into an aircraft, and it will not affect the aircraft itself. Something that you need to know, if you don't know, is that when you want to get some electricity in an aircraft, you need to get this electricity from the engine. And if you take some electricity from the engine, you reduce the power of the engine. So the engine mechanics, they always deny every access to energy in the aircraft. You take the minimum and that's all. this device that was designed in Toulouse actually is sustainable and can be put on an aircraft. So in this project, there were actually experiments done in Toulouse for subsonic flow and small scale wings. In much smaller scale, but for transonic flow, it was done in University of Danks, and also in Polittico di Milano for also incompressible flow, so small velocity but much higher configuration, much bigger configuration. And of course, we did a lot of simulation, and I'm going to focus on the simulation. All the results that I'm going to present to you, actually, they have been validated. We have compared everything with the numerical, with the experimental data, but I will not show any comparison. So you have to trust me that what I show you is correct. So we use an in-house solver, which is a very old solver developed in the 80s, and then since then it has been used in many projects. It was formerly used by Airbus to design the aircraft, so Airbus have moved to another software, and now with my colleague Jan Vos at CFS Engineering, we are the main developer of this software. It's a multidisciplinary software in fluid mechanics, and basically we can do almost everything in fluid mechanics from combustion. It's also one of the last solver in Europe to be able to deal with hypersonic flow, ablation, and so on. So you have here an overview of everything that we can do. It's a compressible solver that can do incompressible flow. It is, of course, massively parallel. So this is actually the experimental part where you have a small wing, and at the end of the wing we put some piezo actuators, and these piezo actuators, they can vibrate to a frequency up to 700-800 Hertz. Very small deformation but very high frequency. We patch all this together, and we have actually a trailing edge that can oscillate. Very small deformation. Basically, the deformation that we had were around 0.7 millimeters of amplitude. I guess you can still hear me. So you see, we can have a very small deformation, but at very high frequency. So on this movie, it's not moving very fast, but we can go up to 700 Hertz. So this is done with piezo actuator. We can use also shape memory alloys. So shape memory alloys allow us to have much bigger deformation, but at a very, very low frequency. But we can actually bend the wing with a larger deformation. Numerically, how do we do that? Basically, we just impose actually an oscillation of our trailing edge. Okay, it's a square for polynomial function, and we apply actually an oscillation in time. So first result is on an experiment that was done in Toulouse. So it's a small wing, 0.7 meters. Span is, span is 0.6, and the Reynolds number is 1 million, which is far low, a very small Reynolds number, but at least very easy to do in a numerical way. So this is some experimental result that was performed. So we have here actually particle image velocimetry, and we put actually, we made some post-treatment, and we introduced some particle to see actually the flow, and what we are interested in is the basic physics. So you have a detachment here that you can see, and behind this detachment you have also in red and blue, the mixing of the two of them is called the shear layer. Okay, so we have a very complex interaction between a von Karman vortex, which is detached periodically here, and a shear layer instability. And this shear layer is a separation between what we call the non-turbulent region, because outside the flow there is no perturbation at all, so the flow is non-turbulent, and the flow is turbulent around the body and in the wake. So this is very fast, the grid that we use. We reproduce the experimental data. The grid is it's quite reasonable, 10 million cells, and we obtain this kind of result where we see we are able to capture with, so the difficulty here is the turbulence model. We cannot do a direct numerical simulation. We cannot use large eddy simulation like was presented by Professor Condell, because it's feasible, but it's too expensive, and we need a grid which will be more 200 million cells than just 10 million. 200 million cells. So with this model that we developed during my PhD long time ago, we are able actually to reproduce this vortex, and we are able actually to have the vortex shading behind, and what we see is that we have detachment and start it beginning with a kind of 2D flow, and then it starts to ondulate and it becomes fully 3D. This is something that is very classical actually in wakes, and so very well documented. We have done that for a long time on any kind of Reynolds. Now, we're interested and we want to improve the flow, so we put our oscillation. So we have here a morphing which is 300 Hertz, 0.7 millimeters of oscillation. So you have here what we and you have on the left here a picture of the flow, initial flow, and on the right, this is the result of the flow. So as this frequency, which is the optimal frequency for this kind of flow, where you see actually that you have a 2D sequence of vortices. Okay, so the flow is still unsteady, the flow is still turbulent, but the fact that it is 2D actually, the flow remains 2D, and this will increase actually the performance of the aircraft. You have a picture here that showed actually that you are able to sustain a 2D flow or a 2D wake much longer than the initial case. And this is important because even if it is a wake, like I said, this wake, because the flow is incompressible, actually the perturbation here, any kind of perturbation will travel back because the flow is incompressible at an infinite velocity. So this means that everything that happens in the wake will affect your lift, your drag, and everything. And so we have tried to understand actually why we have this 2D road and so on. So actually we have a kind of locking phenomena. So this is the initial flow that we have with, so we have introduced here some particle in our simulation, and you see actually the formation of the wake. And so it's in the middle plane, but you have a destructuration in the 3D dimension. And here actually you have something that is much more regular. And also what is interesting also is that the thickness of the wake is smaller. And also this is also an important thing actually to reduce the drag essentially. So we made some much precise simulation with a much bigger grid, 6 times bigger, which requires much more computing time. So nice picture. We represent here actually the Q criteria, which is one way to visualize the structure. And so on the top here you have the unsteady flow without any morphing, and here you have a picture with morphing on the right and without morphing on the left. So you see, you can still see here actually the 2D vortices that are ejected from the wake. So the vortex here is ejected, but this vortex actually is destructurated in 3D. Otherwise, here it remains quasi two-dimensional. So so the Q criteria is a nice stuff, but we can take different value of the criteria to see different kind of vortices, and we see in a very detailed. So what you see also is that the flow is complex in a way that you have, of course, these vortices that are two-dimensional, like basically this is a vortices that you see in the morning. You take your spoon in your coffee, you play with your coffee, and you see some vortices. This is exactly the same stuff, the von Karman vortices in 3D, but you have also some vortices that are interconnecting the different row of vortices, and this become more and more complex with the Reynolds number. So here just a picture to show that finer grid is supposed to give you a much better result. It is of course more expensive, but even with our methodology, OOS, 2D grid, so this is a detached eddy simulation, so it's a mix between basically a Rounds model or a U-Rounds model and large eddy simulation. So something much more precise, much more costly also, but here with our simple model, 6 times the smaller grid, we still capture everything that we can see in the more refined grid, more refined simulation, except that we have a 2D flow actually that is, I would say, that remain more longer than the DES case. So what about the performances? Okay, like I said, that I told you that the idea was to increase the performance. So with this morphing, 300 Hertz on this small wing, we are able to achieve 4% of increase in the lift, 2% of loss in drag, okay, not very good, and the lift to drag ratio, an increase of 1%. So the most interesting part is this 4%. Why is it interesting? Because this is actually the wing that we use here is Airbus A320. So the most sold aircraft in the world. This wing is optimized already. And for Airbus, for example, there is no way that by just changing the shape of the wing or without morphing, that they achieve actually this, because the wing is already super optimized. So this is very interesting for Airbus because at a very low cost, they are able to get 4% of lift. Okay, a small, just maybe it's a 2D extruded case and it's not a real wing. Okay, we are going to do some simulation on real wing and we are going to see that we have less than 4%. Okay, so now we did some also case on a larger scale. So now it's 2.7 meters and so it's a 2-element airfoil. Okay, and we are going to look at the takeoff configuration. So we had the experiment in Politico di Milano. We had the simulation in Strasbourg and Toulouse. This is a picture of the simulation. We have the good comparison between numerics and experiment. And we are going to look now at the morphing. Okay, so again, what we morph is what we call the flap, okay, that is used at the taking off and the landing. And this is an animation of the morphing. So this is the result for the different morphing, still 0.7 millimeters in terms of amplitude of the morphing. And you see that the more you increase the frequency, the more you are able actually to almost kill the instability in the wake. If we look at the animation, we see that we have actually the trailing edge. So here the flow is more complex, okay, if I come back to, because here you have the flow, one part of the flow is coming on the top, one part is coming on the bottom between the two wings, okay, so there is a mixing region here, there is also a flow behind, and then you have a wake actually with 3 interactions, so it is a little more complex, so that's why actually it takes a little more time. It's not the same kind of instability also, but 300 Hertz we are able to remove that. Also an interesting part is that when something in fluids actually, is that when you have a vortices is a change of velocity. Bernoulli tells you that a change of velocity is also a change of pressure, and pressure it's sound. Okay, and here we have a spectral density of the pressure, and you see that when you add actually the morphing in red, you have a lower peak on the spectral density of the pressure. So you decrease the noise. And this is extremely important because one thing that is difficult today actually is to comply to, for the airport actually to comply to the noise, regulation of noise, okay? The good example of that was the Concorde actually. The Concorde stopped not because of the accident, the Concorde stopped because the regulation in the US, they decreased the admissible noise at JFK airport. And it was not possible to modify the Concorde, so it could not land anymore. So you have an aircraft that cannot land or take off. So this noise and this regulation are becoming more and more strict. So with this technology, you can reduce the noise slightly in the wake, so reduce the noise, or what we call the aerodynamic noise of the aircraft. And also, we have also, so this is something that we did a long time ago, but we studied, and this is something very common, these 2D vortices actually, they have also the ability to merge together, we create a vortex dislocation, which also create noise. And here, when we add our morphing, we reduce this dislocation. In terms of aerodynamic performances, here on the lift, we can have up to 1.6%, no, sorry, 0.57% of increase. So it's a lot and it's not a lot. It's not a lot because we are just talking about the flap, okay? And the flap by itself, it does not represent all the lift of the wing. So still interesting. Another technology now, we are going to see if we use now cumbering. So if we use shape memory alloy to deform the flap. So this is feasible on an experimental point of view. Okay, maybe I can switch to that. So we did some stimulation with different position, and we studied actually the influence of the cumbering of the flap. And we see that the more we increase the cumbering of the flap, which is, I would say, something that is obvious and very intuitive, you increase the lift. You also increase the drag a little. And the conclusion, if you increase the Reynolds number, so we did simulation also at a higher Reynolds number, 7 million, then the increase actually of the lift to drag ratio, you see that you increase in most of the case, except for the position 4 at 0 degrees. But if you look at 2, 4, 6 degrees, you have, so the higher is the Reynolds number, the more interesting is the morphing. Oops. So if we take the case, so what does it mean here? It means that we have a reference case of taking off at 8 degrees. We can obtain the same performance in terms of drag and lift, so lift to drag ratio. I would say we have an increase of 8% by having an aircraft that will fly at 4 degrees and to convert the flap. So when you have a flap in an aircraft, you have different position of the flap, okay? So that is already working, but the flap is a wing that it's a geometry that does not change its shape. The idea of the hybrid morph, or this kind of morphing, is actually to adapt the shape of your flap or your wing later to every condition. So a little like a bird. So that was still also on a 2D configuration. So we take a full aircraft, so Airbus 320, and we put some morphing actually only on the flap. So we started with first change of shape, cumbering, okay, and we see that this is a real case, real Reynolds number, so still small, okay. The issue is that it's very difficult to make the simulation at real Reynolds number, but actually for taking off, it is still possible. So at the first stage of the taking off, and you see where we have the same phenomena, okay, that using the, no, that's the lift actually, and that's the gain in lift ratio. That's a mistake here, let me see. So we can increase, we still have an increase of 2%, less than what we have earlier, but this is now the full aircraft, okay? So by changing the shape of the flap with a technology that is achievable, we can increase the performance of the aircraft. So we did on the aircraft first the shape memory, using shape memory alloy. Now we are going to mix actually the shape memory alloy and the piezo actuator. So basically what we are going to try to mimic actually exactly what a bird is doing. Of course, if you look at the feather of a bird, it's not vibrating at 300 Hertz, okay? But still, at the end, it's something that is, they can of course change the cumbering, the geometry, but they can also have this oscillation at the wake. So here what we have is we can play with the cumbering and we superpose actually the trailing edge vibration. So we don't mention here, of course, the numerical technology that is behind, but it's of course not something that is very easy to implement in numerical software, but it's feasible. The result is what it is. It is less interesting, that the cumbering here is less important, so we have an increase. I just keep this graph. We have an increase of the lift to drag ratio around 0.5% in this case. The angle of attack, for different angle of attack actually. So On this configuration, I would say that the vibration is counterproductive, because before we had we have something between 2%, and here you only have 0.5. So in this case, this oscillation that we have is not very efficient, and we have to more. It's a result, and it's not something that is very strange, because we apply here a frequency that was around 300 Hertz, but so far what we don't know and what we are working on now is maybe you should use, for example, 300 Hertz in this region, but when you come to this region here, you should increase or decrease the frequency. So that's what we call vobulation, actually. And we are working now, but I don't have the result. We don't have the result yet, but we are working actually on changing the frequency of this oscillation in the spanwise direction to adapt to the flow itself, to be more efficient. Transonic speed, like I said, so these are simulations that have been done for a long time ago. This is a phenomena that a lot of people and for a long time has been working on. So you have a shock, okay, so with the Mach number is here 0.7, okay, so you have an increase of the velocity until this dark region here, where the velocity decrease and the pressure increase, and because of the pressure increase behind, you have a thickening of the boundary layer, which is not good at all, because it's a recirculation region, okay, and you have a buffeting effect, so the shock is oscillating and going forward and downward, and when it goes forward, you have an increase of the shape of the boundary layer, a large detachment that you can also see here, and of course a decrease of the aerodynamic quantities, especially the lift, and basically what you have is that you have your wing going up and down, up and down, up and down. So, here is for different, so what you see here actually is that, yes, we introduce actually some particle in this region. So this is without any morphing, and you see that we have actually a boundary layer that is very big with a strong detachment and a vortex shading behind, and when we introduce this morphing at the trailing edge, here we have a very drastic reduction of the detachment, and at 350 Hertz we remove the instability in the wake. So basically what we have been able to do is that we have almost, okay, it's not completely removed, but we are basically, and we see that on the next slide, we see that now this is the shock and the position of the shock, and you see that the position of the shock is very restrained compared to what we had before, where it can go up to the leading edge. Also, in this case, the morphing frequency can be, experimentally, it can go up to 700 Hertz. Practically, this is very difficult, okay? This is something that this study actually is only experimental, because to have a piezo actuator that is able to resist a compressible flow in real condition and vibrate to 730 Hertz doesn't exist yet. It will break. So this was in the SMS project and the continuity. Now we have a French project called MBIA, and our colleagues actually in Strasbourg are working. What we want to do now is we want to not only have this oscillation at the trailing edge, but we want to have the oscillation everywhere on the wing. We want to basically build a kind of shark skin on the wing, and so a shark is built of very, very small winglet, okay, and we want to have a vibration of this winglet. I'm saying a shark, so here it's more with the idea is that the jelly moon or the manta ray. Talking about, for example, the shark, there have been some experiments. The shark is a very extraordinary fish, if we can say that, because it's very quiet. And if when you look at the skin of the shark, it's absolutely not smooth at all. So we try to mimic that on a wing, and it works. If you put a kind of skin shark on a wing, you reduce the drag, you increase the lift. It's working perfectly well. It's not usable at the long term because because it's very rough, and as soon as you have dust on this roughness, then the result is worse than on the initial shape. So NASA did some experiment on that. The shark skin is very nice, but you have to clean it during the flight, and that is not possible. So here we want to do the same stuff, but now by just having some vibration everywhere, and of course it's a 3D configuration. The idea would be to have an artificial intelligence that will control the vibration everywhere. If we take the piezo actuator can act as an actuator, but it can also be pressure measurement system. Okay, so you can have some measurement somewhere, have a reverse flow, I mean a reverse engineering to see what is happening on the flow, and then use the appropriate control to apply, so frequency and amplitude to apply everywhere. So that's the 20 years from now goal that we have. So in this project, actually, the colleague in Strasbourg, they are trying to find the new material for this that will be able to sustain very heavy loads at high frequency. And I'm working with Abderrahman on the simulation part. But we started with something very simple, is to have what we call a traveling wave. So it's a wave actually that will propagate on the skin at different regions. So we try different waves. So you see that the amplitude is very small at the beginning, and the amplitude is higher here, and you have both actually an oscillation, and this oscillation is traveling downwards. So we play with different frequency, different wavelength, different position of this, and we obtain quite good result. And what we see actually on these two pictures, so initially like we have seen before, so this is on the 1 so one where you have this vortex shading at the end. You see here that you have a reverse flow. You have here what is in blue actually is negative velocity. You see that the flow is going downward, and when you apply this oscillation actually, you reduce and you completely remove. Actually, this is a steady picture at time 0.059 seconds. You remove actually the vortex, so there is no more reverse flow. In terms of performances, again, we played with different position, different wavelength, different frequency, and the winner is position 4 at 300 Hertz and for a wavelength of 6 centimeters. So, to conclude, we are able to play with the secondary instability to reduce the growth of the secondary instability, to suppress three-dimensionality in the wake. We are able to produce a wake that is thinner, that is smaller than the original wake. We can increase the lift, decrease the drag, and sometimes increase the drag. When it's taking off, it's not good, but if we take, for example, the landing side, to increase the drag when an aircraft is landing, that's not really a problem. And we can decrease the noise. And thank you for your attention. So just to mention that what we are doing now actually is that we are working, so Abderrahman, I would say, because I'm not doing that, I'm too old to do machine learning and artificial intelligence, but he's actually building models to be able to guess with an artificial intelligence system all the configuration of this flow to put that actually into a controller. So we have a new European project that will start with the same partner almost in December, where we intend to do that, to do actually the morphing on the full aircraft now, on the full wing. And we have one of the partners is Hoarau, and Hoarau is working on the automatization of the control with using the result of machine learning and so on. So we are playing also with, like we talk about the vobulation, but we are also doing some simulation to see if we increase in time the frequency, and more difficultly to do is if we change the frequency in the span-wise direction. Thanks a lot.
Thank you.